In this video, we will be introducing the concept of molecular orbital theory, which builds upon our previous valence bond theory. While valence bond theory does do a much better job than Lewis theory at predicting certain parameters, such as the bonding schemes, bond strength, bond length, and the bond rigidity, it does fall short in some aspects. There are still properties that valence bond theory is unable to correctly predict, such as the magnetic behavior of oxygen. In addition, valence bond theory presumes that electrons are localized in orbitals on the atom in the molecule and does not account for delocalization and can also not fully describe the phenomena of resonance structures. So what we need is a modification to the valence bond theory that will enable us to hopefully describe both magnetic behavior of molecules and be able to account for things like delocalization of electrons through resonance structures. Molecular orbital theory, or MO theory, can be thought of as a modification of the valence bond theory. However, molecular orbital theory applies Schrödinger's wave equation to the concept of the molecule in order to calculate a set of molecular orbitals as opposed to atomic orbitals. The equations for these molecular orbitals are estimated. The estimated solution is evaluated and then adjusted until the energies of the orbitals is minimized. One of the ways that molecular orbital theory differs from valence bond theory is that it treats electrons as belonging to the whole molecule, so that the orbitals belong to the entire molecule, not just being made up between two atoms that are bonding together. This enables us to describe more properly the phenomena of resonance structures as well as account for delocalization of electrons through multiple adjacent double bonds. The initial approach to adding these atomic orbitals together will look somewhat like our valence bond theory. Our simplest guess starts with the atomic orbitals of the atoms being added together to make a molecular orbital. This is called the linear combination of atomic orbitals. The reason it is linear is we are doing a summation of our two wave functions, adding them together and getting an orbital that looks very similar to what we had for valence bond theory. It is a weighted sum based on how much of each one of the two atoms you are adding together. The bond is still called a sigma bond when you have direct overlap, and this here would be an example of a sigma 1s bond. This would be adding together two sets of 1s orbitals from something like a hydrogen atom in order to come up with a sigma bond through their bonding regime. Because the orbitals are now being treated as wave functions can combine either constructively or destructively. If you think back to our discussion on wave-like behavior of light, we had constructive and destructive interference, where if we added two waves together, they could either increase their amplitude through constructive interference, or they could destructively interfere and to some extent nullify each other. What we see through constructive interference is what we had been looking at with our valence bond theory, where we add the two wave functions together and come up with a combined orbital that is bigger than the individual orbitals. If we add them together and there is destructive interference, we could think about this in two ways. One is taking one of our orbitals and subtracting the other. So we would have one that has a positive amplitude and one that has a negative amplitude. So take the positive amplitude one minus the other one. Or you could think about this as having one that has a positive amplitude and the other that has a negative amplitude and adding them together. Mathematically, it's the same thing. You either have one orbital minus the other or one orbital plus the negative of the other. Mathematically, it's the same thing. The result is Where the two overlap, they cancel out, and so you will have two orbitals with a node in between. The node is a region of space where the electron cannot exist. Because there is a node between your two atoms, this inhibits bonding. The inhibition of bonding is called antibonding. When the wave functions combine constructively, the resulting molecular orbital has less energy than the original atomic orbitals. These are called bonding molecular orbitals, and we designate them as either sigma or pi, depending on, again, whether we have direct overlap, which would be a sigma bond, or indirect overlap via orbitals overlapping from bonds that are perpendicular to the interatomic axes. The pi bonds are the same pi bonds as we had when we were looking at valence bond theory. Most of the electron density for these constructively interfering atomic orbitals is between the two nuclei. Part of the reason why the constructive interference, making the orbitals bigger and creating bonding orbitals, part of the reason why it is less energy is the electrons now have a wider range of space to occupy. This creates stability and decreases the overall energy of that state. When the wave functions combine destructively, however, the resulting molecular orbitals have more energy than the original atomic orbitals. It takes more energy to put electrons into the antibonding orbitals, which is what we will call wave functions that combine destructively. They will be called antibonding molecular orbitals. The way that we will designate them is using our sigma and pi as before. However, we will put a star next to the symbol. The point of the star is to designate these as antibonding orbitals. So if we have direct overlap, but it is destructively interfering, it is called a sigma star antibonding orbital. And if they are destructively interfering through orbitals that are perpendicular to the interatomic axes, they would be called pi star or pi antibonding orbitals. Most of the electron density is going to be outside of the internuclear axes. This is because between the two atoms there will be nodes where the two orbitals destructively interfere and where we will not be able to find any electron density. Looking at a pictorial representation of two sets of 1s orbitals combining together, we could have two 1s orbitals that constructively interfere. That means where they overlap, they add together. We would get our bonding molecular orbitals. This is the same shape that we had with the valence bond theory. However, where the valence bond theory fails is it does not predict the destructive interference, where we have the two wave functions destructively interfering with each other, resulting in our antibonding orbital. The antibonding orbital, because of the node that is placed between the two atoms, that node increases the energy of the resulting molecular orbital. This causes it to be higher in energy than the two orbitals that were used to combine together to get our antibonding molecular orbital. Again, the labels that we will be placing on our orbitals are a sigma 1s for our constructive interference, or our bonding molecular orbital, and a sigma star 1s for our destructive interference, which is our antibonding molecular orbital. What molecular orbital theory does for us is that it enables us to explain why bonds occur. Electrons in bonding molecular orbitals are stabilized, resulting in lower energies than the individual atomic orbitals. As we will see in subsequent videos, it also helps us explain why some bonds won't form, and that's because we have antibonding molecular orbitals that destabilize bonds. These antibonding orbitals are higher in energy than the atomic orbitals. The electron density is located outside of the internuclear axes, which inhibits bonding. And the electrons in antibonding orbitals cancel the stability gained by the electrons in the bonding orbitals.